Hey there, future innovators and curious minds. Get ready to embark on an incredible journey through the world of Grade 10 science and technology. It's a place filled with mind-blowing discoveries, fascinating facts, and the tools to understand how our universe works. Science isn't just a subject in school, it's a way of looking at everything around you with wonder and asking why and how. From the tiniest particles to the vastness of space, science helps us unravel mysteries and solve real-world problems. So buckle up your brain belts because we're about to explore some seriously cool stuff together. This year, we're going to dive deep into three major themes. First, we'll explore Earth and space, uncovering the secrets of our planet and its place in the cosmos. Think frozen grounds, mighty oceans, and the energy that powers our world. Then we'll venture into the material world. The amazing realm of chemistry will look at how substances mix, react, and form everything we see and touch. We'll even learn the language of elements with the periodic table. It's all about understanding what stuff is made of and how it changes. Next up is the technological world. This is where science meets creativity and invention. We'll learn about the principles of engineering, how machines make our lives easier, and the magic of electricity. We'll also investigate different materials and how we use them to build incredible things, from towering skyscrapers to tiny computer chips. Technology is all about applying scientific knowledge to design, build, and create solutions. It's about making things work and work better. Get ready to think like an engineer and a designer. Throughout this adventure, remember that science is for everyone. You don't need to be a genius to understand it. You just need curiosity and a willingness to learn. We'll break down complex ideas into simple, easy-to-grasp concepts. We'll use real-life examples that you can see every day, and most importantly, we'll have fun doing it. Science is a hands-on, minds-on experience. So let's get started on this ultimate crash course and unlock the wonders of science and technology together. Consider the following. Let's start our journey with something super cool. Literally, we're talking about permafrost. Permafrost is ground, like soil or rock, that stays frozen for at least 2 years straight. Think of it as a giant natural freezer beneath the Earth's surface, mainly found in cold regions like the Arctic and Antarctica, and at high altitudes. It can be a few inches deep or extend thousands of feet down. This frozen layer is a critical part of Earth's systems, influencing landscapes, ecosystems, and even the global climate. Understanding permafrost is super important, especially in our changing world, because when it thaws, it can cause big problems. Why does permafrost matter so much? Well, for starters, many northern communities build their homes, roads, and pipelines on permafrost. When it thaws, the ground becomes unstable, like trying to build on mush. This can cause buildings to sink, roads to crack, and pipelines to break, which is a huge issue for people living there. Thawing permafrost also releases ancient organic material that has been locked away for thousands of years. When this material thaws and decomposes, it releases greenhouse gases like carbon dioxide and methane into the atmosphere, which can make our planet warmer. It's a bit like opening an old freezer and letting out trapped gases. Now let's connect permafrost to climate. Climate refers to the long-term weather patterns in a particular area, not just today's weather, but the average weather over many years. Our Earth's climate is currently warming, and this warming is causing permafrost to thaw at an alarming rate. This creates a feedback loop. As the Earth warms, permafrost thaws, releasing more greenhouse gases, which then cause even more warming. It's a cycle we need to understand to address climate change. Scientists study ice cores from permafrost regions to learn about past climates, giving us clues about our planet's history. Finally, let's talk about the greenhouse effect. Imagine a greenhouse for plants. The glass roof lets sunlight in, warming the inside, but it also traps some of the heat from escaping. Earth's atmosphere does something similar. Certain gases, called greenhouse gases like carbon dioxide, methane, and water vapor, act like that glass roof. They let sunlight pass through to warm the Earth's surface. The Earth then radiates heat back. But these gases trap some of that heat, keeping our planet warm enough for life. This is a natural and essential process. However, human activities like burning fossil fuels are adding extra greenhouse gases, making the blanket thicker and trapping too much heat, leading to global warming. Water everywhere. It's essential for life, and it's constantly on the move. Let's start with watersheds. A watershed, also called a drainage basin, is an area of land where all the water that falls as rain or snow or flows from streams and rivers drains into a common outlet. This outlet could be a larger river, a lake, or an ocean. Think of it like a giant bathtub where all the water collects and flows towards the drain. Watersheds can be tiny, like the area draining into a small pond, or enormous, like the Mississippi River watershed, which covers a huge part of the United States. Why are watersheds so important? They provide us with drinking water, water for agriculture and industry, and habitats for countless plants and animals. What happens in one part of a watershed, like pollution from a factory or deforestation on a hillside, can affect the water quality and quantity downstream for everyone. That's why protecting our watersheds is crucial. For example, if farmers use too much fertilizer, the excess can wash into rivers and lakes within the watershed, causing algae blooms that harm aquatic life. So, healthy watersheds mean a healthy environment and healthy communities. Now let's dive into the oceans and talk about salinity. Salinity is the measure of how much dissolved salt is in water. Ocean water is salty because rivers carry dissolved minerals, including salts, from rocks and soil on land into the sea. When ocean water evaporates, the water turns into vapor, but the salts are left behind, making the remaining water saltier. The average salinity of the ocean is about 35 parts per thousand, meaning if you had 1,000 grams of seawater, 35 grams would be salt. Salinity isn't the same everywhere. It can be lower near river mouths where fresh water flows in, or higher in hot, dry areas where evaporation is high. Salinity, along with temperature, plays a huge role in ocean circulation, the large-scale movement of water in the oceans. These movements are like giant conveyor belts, distributing heat around the globe and influencing climate. Colder, saltier water is denser or heavier and tends to sink, while warmer, less salty water is less dense and rises or stays near the surface. This difference in density drives deep ocean currents. Surface currents, on the other hand, are mainly driven by winds. For example, the Gulf Stream is a warm surface current that brings milder weather to Western Europe. Understanding these currents helps us predict weather patterns and understand marine ecosystems. Now, let's switch gears and talk about energy resources, the sources of power that run our homes, cars, and industries. We can broadly classify energy resources into two types: non-renewable and renewable. Non-renewable resources are those that exist in limited amounts and cannot be replaced once they are used up, or take millions of years to form. The main examples are fossil fuels, coal, oil, and natural gas. These were formed from the remains of ancient plants and animals. We also have nuclear fuels like uranium, which are mined. These resources have powered much of our modern world. Renewable energy resources, on the other hand, are naturally replenished on a human timescale. This means they won't run out if we manage them properly. Think of solar energy from the sun, wind energy captured by turbines, hydropower from flowing water, geothermal energy from the Earth's internal heat, and biomass from organic materials like plants and wood. Using renewable energy is crucial for a sustainable future because it helps reduce our reliance on finite fossil fuels and lessens the environmental impact, such as the emission of greenhouse gases that contribute to climate change. For example, solar panels on a roof can generate electricity without producing any pollution. Welcome to the material world. Let's start by exploring solutions. A solution is a special type of mixture where one substance dissolves completely into another. The substance that dissolves is called the solute, and the substance that does the dissolving is called the solvent. Usually we think of solids dissolving in liquids, like sugar dissolving in tea. But solutions can also be gases in liquids, like carbon dioxide in soda, or even solids in solids, like alloys such as brass. The key thing is that a solution is uniform throughout. You can't see the separate parts. Now, how much solute is in a solution? That's where concentration comes in. Concentration tells us the amount of solute present in a given amount of solvent or solution. If you dissolve a little sugar in your tea, it's a dilute solution, meaning it has a low concentration. If you dissolve a lot of sugar, it's a concentrated solution, which means it has a high concentration. Calculating concentration is important in many fields. For instance, doctors need to know the correct concentration of medicine, and chemists need precise concentrations for experiments. Next up is the pH scale. The pH scale measures how acidic or basic a solution is. It ranges from 0 to 14. A pH of 7 is neutral, like pure water. Solutions with a pH less than 7 are acidic. The lower the number, the stronger the acid. Lemon juice and vinegar are examples of acids. Solutions with a pH greater than 7 are basic or alkaline. The higher the number, the stronger the base. Soap and baking soda are examples of bases. The pH scale is logarithmic, which means each whole pH value below 7 is 10 times more acidic than the next higher value. For example, pH 4 is 10 times more acidic than pH 5. So what makes a solution acidic or basic? It all comes down to ions, specifically hydrogen ions, or H+, and hydroxide ions, or OH-. Acids release hydrogen ions when dissolved in water, while bases release hydroxide ions or accept hydrogen ions. These ions are atoms or molecules that have gained or lost electrons, giving them an electrical charge. The presence of these charged particles, or ions, in a solution allows it to conduct electricity. This property is called conductivity. The more ions a solution has, the better it conducts electricity. For example, salt water, which has lots of sodium and chloride ions, conducts electricity well, while pure water with very few ions is a poor conductor. Let's dive into the exciting world of chemical reactions. A chemical reaction is a process where substances, called reactants, are transformed into new substances called products. During a reaction, the atoms in the reactants rearrange themselves to form different molecules. Think of it like taking Lego bricks from one model and using the same bricks to build a completely new model. There are many types of chemical reactions happening all around us and even inside us all the time. Understanding these reactions helps us make new materials, produce energy, and sustain life itself. One common and important reaction is combustion. Combustion is basically burning. It's a rapid reaction between a substance and an oxidant, usually oxygen, to produce heat and light. When you burn wood in a fireplace, that's combustion. The wood and oxygen are the reactants, and the products are ash, smoke, which contains carbon dioxide, and water vapor, heat and light. Another vital reaction is photosynthesis, which happens in green plants. Plants use energy from sunlight to convert carbon dioxide from the air and water from the soil into glucose, a type of sugar which is their food, and oxygen. This is how plants make their own food and also release the oxygen we breathe. Another important type of reaction is neutralization. This occurs when an acid and a base react with each other. When they combine, they neutralize each other's properties, producing a salt and water. For example, if you have an upset stomach due to excess stomach acid, which is hydrochloric acid, you might take an antacid, which is a base like magnesium hydroxide. The antacid neutralizes some of the stomach acid, relieving your discomfort. The products of this reaction are magnesium chloride, which is a salt, and water. Neutralization reactions are crucial in chemistry labs, industrial processes, and even in our bodies to maintain proper pH balance. Now, a super important rule in all chemical reactions is the law of conservation of mass. This law states that in a chemical reaction, mass is neither created nor destroyed. This means the total mass of the reactants before the reaction is equal to the total mass of the products after the reaction. Atoms are just rearranged, not lost or gained. If you were to carefully measure the mass of wood and oxygen before burning, and then measure the mass of all the ash, smoke, and gases produced, you'd find the total mass remains the same. This fundamental principle helps scientists balance chemical equations and understand the quantitative relationships in reactions. It's a cornerstone of chemistry. Let's explore the building blocks of all matter, the elements. And our map for this exploration is the amazing periodic table of elements. The periodic table is a chart that organizes all known chemical elements in a specific order. Elements are pure substances that cannot be broken down into simpler substances by ordinary chemical means. Each element is made up of unique atoms. The table arranges elements by their atomic number, which is the number of protons in the nucleus of an atom of that element. It's like a super-organized library for chemists, with each element having its own special place and properties. The periodic table isn't just a random list. Its organization tells us a lot about the elements. Elements are arranged in rows called periods and columns called groups or families. Elements in the same group have similar chemical properties because they have the same number of valence electrons. These are the electrons in the outermost shell of an atom, which are involved in chemical bonding. For example, Group 1 elements, known as the alkali metals like lithium, sodium, and potassium, are all highly reactive metals. Group 18 elements, the noble gases like helium, neon, and argon, are very unreactive because their outermost electron shells are full. Understanding the periodic table helps us predict how elements will behave and react with each other. For instance, elements on the left side of the table are generally metals, which tend to be shiny, good conductors of heat and electricity, and malleable, meaning they can be hammered into shapes. Elements on the right side are generally non-metals, which are often dull, poor conductors, and brittle. In between, there are metalloids, which have properties of both metals and non-metals. Knowing these trends allows scientists and engineers to choose the right elements for specific applications, like using copper, a metal, for electrical wires, or silicon, a metalloid, for computer chips. We also talked about ions earlier. Remember, ions are atoms or groups of atoms that have an electrical charge because they have lost or gained electrons. The periodic table can help us predict what kind of ions an element is likely to form. Metals, especially those in groups 1 and 2, tend to lose electrons to become positively charged ions called cations. For example, sodium loses 1 electron to become Na+. Non-metals, especially those in groups 16 and 17, tend to gain electrons to become negatively charged ions called anions. For example, chlorine gains 1 electron to become Cl-. This tendency to form ions is key to how elements bond together to form compounds. Now let's shift into the technological world and explore engineering. Engineering is all about using scientific principles to design and build things, machines, structures, systems that solve problems and make our lives better. There are many branches of engineering, but we'll touch on mechanical and electrical engineering basics. Mechanical engineering deals with designing, building, and operating machinery. Think of car engines, robots, power plants, and even simple tools like levers and gears. It's about understanding forces, motion, energy, and how physical systems work together. Let's talk about motion. Motion is simply a change in an object's position over time. There are different types of motion. Rectilinear motion is movement in a straight line like a bowling ball rolling down the lane. Rotational motion is movement around a fixed axis like a spinning top or a wheel turning. Oscillatory motion is repetitive back and forth movement like a pendulum swinging or a guitar string vibrating. Understanding these types of motion is fundamental for engineers when they design moving parts in machines. For instance, the pistons in a car engine undergo rectilinear motion while the crankshaft undergoes rotational motion. Engineers use motion systems to control and transmit motion and forces. These systems often involve simple machines, which are basic mechanical devices that change the magnitude or direction of a force. Examples include levers like a seesaw or a crowbar, pulleys used in cranes to lift heavy objects, inclined planes like a ramp, wedges, screws, and wheels and axles. Complex machines are often made up of combinations of these simple machines. For example, a bicycle is a complex machine that uses wheels and axles, levers, such as handlebars and brakes and gears, to make riding easier and faster. Speaking of making things easier or faster, let's look at speed and gear ratios, which are key concepts in mechanical engineering. Speed tells us how fast an object is moving. We can calculate it by dividing the distance an object travels by the time it takes to travel that distance. For example, if a car travels 100 kilometers in 2 hours, its average speed is 50 kilometers per hour. Gears are toothed wheels that mesh together to transmit rotational motion and torque, which is turning force. A gear ratio is a comparison of the number of teeth on 2 connected gears or their rotational speeds. For instance, if a driving gear has 20 teeth and the driven gear has 40 teeth, the gear ratio is 2:1. This means the driving gear will turn twice for every single turn of the driven gear, resulting in increased torque but decreased speed on the driven gear. Engineers use gear ratios to control speed and power in machines like cars, bicycles, and factory equipment. Let's get electrified and talk about electrical engineering. This branch of engineering deals with electricity, electronics, and electromagnetism. A fundamental concept is the electrical circuit. An electrical circuit is a closed path that allows electricity, which is the flow of tiny charged particles called electrons, to travel. A simple circuit needs a power source like a battery, conductors such as wires, usually made of copper, and a load, which is a device that uses electricity like a light bulb or a motor. There also needs to be a complete path from the power source through the load and back to the source for electricity to flow. There are 2 main types of circuits: series circuits and parallel circuits. In a series circuit, the components are connected one after another, forming a single path for the current. If one component breaks, like one light bulb burning out in a string of old holiday lights, the entire circuit is broken and all components stop working. In a parallel circuit, components are connected in separate branches. This means the current has multiple paths to flow through. If one component breaks in a parallel circuit, the other components can still operate. Most household wiring is done in parallel, so you can turn on one light without affecting others. Now, let's consider the materials that engineers use. Materials science and engineering involve understanding the properties of different materials and how they can be modified and used to create new products. Properties of materials include things like strength, how much force it can withstand, hardness, flexibility, conductivity, meaning how well it conducts heat or electricity, and density. Engineers choose materials based on the specific needs of their design. For example, airplanes need materials that are strong but lightweight, like aluminum alloys or carbon fiber composites. Cookware needs materials that conduct heat well, like copper or aluminum. Materials can often be modified to enhance their properties or create new characteristics. This can be done through various processes like heating, such as heat treatment for metals, to make them harder or softer, mixing different materials to create alloys like steel, which is iron mixed with carbon, or composites like fiberglass, which combines glass fibers with plastic, or treating their surfaces, for example, galvanizing steel with zinc to prevent rust. These modifications allow engineers to tailor materials for specific applications, making products more durable, efficient, or cost-effective. For example, plastic can be modified to be biodegradable, addressing environmental concerns. Finally, engineers need a way to communicate their designs clearly and accurately. This is where graphical language comes in. Graphical language includes technical drawings, blueprints, diagrams, and three-dimensional models. These visual tools provide detailed information about the shape, size, dimensions, materials, and assembly of a product or structure. For instance, an architect uses blueprints to show builders how to construct a house, and an engineer uses detailed drawings to specify how a machine part should be manufactured. These drawings use standardized symbols and conventions so that anyone trained in reading them can understand the design intent precisely. It's like a universal language for builders and makers. Wow, what a journey we've had through the incredible realms of Grade 10 science and technology. We've explored the icy depths of permafrost, the vastness of our oceans, the power packed into tiny atoms, and the ingenuity behind amazing technologies. From understanding how our planet works to figuring out how to build the future, science and technology are all about discovery, innovation, and making sense of the world around us. Remember, everything we've talked about, from watersheds to chemical reactions to electrical circuits, is interconnected. Science is a giant, fascinating puzzle, and you now have many more pieces. The concepts we've covered are just the beginning. Think of this as your launch pad into a universe of endless learning. The key is to stay curious. Ask questions. Why does that happen? How does this work? What if we tried this? Science thrives on questions. Don't be afraid to experiment safely, of course. And to seek out answers. There are so many resources available, from books and websites to documentaries and science museums. The more you explore, the more you'll realize how exciting and relevant science and technology are to your everyday life. As you review what you've learned, try to connect the dots between different topics. See how understanding the properties of materials helps engineers design better machines, or how knowledge of the greenhouse effect informs our choices about energy resources. Real-world problems often require solutions that draw from multiple scientific disciplines. By building a strong foundation in these core concepts, you're equipping yourself with powerful tools for understanding and shaping the future. You have the potential to contribute to solving some of the world's biggest challenges. So, keep that spark of curiosity alive. Whether you dream of becoming a scientist, an engineer, a doctor, an inventor, or anything else, the knowledge and skills you gain from studying science and technology will always be valuable. This is your adventure. Embrace the challenges, celebrate the discoveries, and never stop learning. The world is full of wonders waiting to be understood, and you, yes, you have the power to explore them. Go forth and be amazing, science superstar. The universe is counting on you.